Hi, welcome back to topic 9.3 here in AP Physics C, Unit 9. So this is on conservation of electric energy. So this is just going to add something to what we've already talked about with conservation of energy. So when you have a charged object moving between two locations with different electric potentials, the resulting change in the electric potential energy of the object is going to be given by the equation delta U sub E equals Q delta V, right? And so there's your difference, right? Your change in electric potential. Again, I mean, it's very similar to when we talk about like MGH, right? So we're just shifting from one height to another. And what are we moving around? In MGH, we're moving the mass around. Here, we're going to be moving the charge around. Okay. So the movement of the charged object between 2 points will result in a change in kinetic energy of the object consistent with conservation of energy. And you can kind of see that string over here, what that kind of looks like. And then, I mean, the way you think about it, right? Conservation energy, delta E equals 0, which means that E is going to be delta K plus delta UG plus delta US plus delta UE, right? All that's going to equal 0. Okay. And again, we're just expanding on the energy that you've already talked about, or we've already talked about in mechanics. In this picture here to the top right, you can just see if the field moves the charge, right? So if it does what it wants to do, like plus wants to go down to negative, then you're going to have positive work done. But if an external force, like what you apply, moves the charge, then you're going to have negative work because you're doing against what it wants to do. Okay. All right. So let's, again, like this is going to be a short video. So let's look at just an example problem. All right. So you got a proton, which has a mass of 1.67 times 10 to the negative 27th. It's going to be accelerated through a potential difference of 4.5 times 10 to the 6 volts. And so the question is, how much kinetic energy was acquired by the proton? And then if the proton started at rest, how fast is it moving? All right. So for part A, we're going to start with our delta U equals Q delta V equation. So this thing to note is that that's already delta V. We don't have to do anything different. And so we're just going to plug in our numbers. So charge on a proton, 1.6 times 10 to the negative 19 coulombs. Then we have the potential difference, 4.5 times 10 to the 6 volts. And so we multiply those two numbers and we end up with 7.2 times 10 to the negative 13th joules. Okay, so that's how much kinetic energy was acquired, because remember, that's going to equal our change in kinetic energy. Okay, and so thing to remember, right, delta K is K minus K initial, K final minus K initial. But this is 0, so that's going to go away. So whatever kinetic energy, change in kinetic energy is, it's the kinetic energy that is acquired by the proton. So what does that do for us? Well, now we can use the kinetic energy equation, K equals 1/2 mv squared. Solve it for V. We get 2K over m, and this is why they give you the mass of the proton, because you need it in this equation. So you get the square root of 2 times 7.2 times 10 to the negative 13 joules, divided by 1.67 times 10 to the negative 27th kilograms. Okay, don't forget to take the square root here, and that ends up being 2.94 times 10 to the 7th meters per second. So just give you an idea how fast that is. C, which is the speed of light, is 3 times 10 to the 8th. So that means that this proton is coming up near, it's about 10 times less than, right, the speed of light. Okay, so that's going to conclude Unit 9, right, on electric potential. And so we look forward to working with you on Unit 10.